differential equations are a very powerful tool to model certain real-life situations. Right. So let me go through a few very simple examples. Right? So let's think of a falling object first. Right. So if an object is falling in vacuum, well, then its acceleration is constant. Well, on the Earth, well, although it doesn't sound right? So, because on the Earth, we cannot have the vacuum and the Earth at the same time. But, well, let's pretend that we don't have any air. So, in vacuum, all objects would fall so that the acceleration is constant, and it is 9.8 meters per second squared. So acceleration is the first derivative of the speed, right? And if the speed is our unknown function that we want to model, then the differential equation tells us that the derivative of this unknown function is simply 9.8. And then, well, if the differential equation looks like this, the derivative of the unknown function is the given function, then we can always just solve it by integrating. But suppose that our object falls in air, like this cat on the screen. Well, then, of course, we should somehow account for air resistance. So how can we do it? What we can do it is that the higher the speed is, the more air resistance, right? So the reason of including this term is because if we have higher speed, V implies more air resistance. And more air resistance means that our falling object accelerates slower. And this is how such a differential equation may look like. So just know that although the first equation is very accurate, right? So this one is just the true equation. So whenever an object falls in vacuum, it satisfies this law of constant acceleration. But in air, it is somehow more complicated. So as far as I know, for some processes, this law is good, but for some other processes, instead, we would have dv dt. The air resistance will be proportional to the square root of the speed. So then we would have 9.8 minus k v squared instead. So here is another example, right? So if you have a cup of very hot coffee, well then its temperature would be a function of time. Right? So as time passes by, coffee cools down. And this Newton's law of cooling, so this is Newton's law of cooling, is that the rate of cooling is proportional to the temperature difference. So the rate of cooling is what? Is nothing else but the derivative of the temperature with respect to time. Right? So the time derivative is the rate of cooling, but since it is the rate of cooling, so the temperature has to slow down, so to decrease, that's why we put a negative sign here, because the derivative of the temperature must be negative, since it is decreasing, the temperature is decreasing, so the coffee is cooling down. Okay. Our third example, well, imagine a colony of bacteria. So population is P of T. So P is the population, T is time, and this P of T is measured, well, it's actually mass of all bacteria. So it is measured in, I don't know, probably milligrams or something. So I don't know how exactly bacteria weigh, but it's not the amount of bacteria, but it's rather the total mass of bacteria, right? So it is really a continuous quantity. It's not a discrete quantity. Well, and then I think it's quite clear that the more bacteria we have, the faster they multiply, and that the population growth rate is proportional to population itself. Right? So the growth rate is the derivative of population with respect to time. So mathematically, we have this differential equation. The derivative of the unknown function equals some constant times the unknown function. Well, but of course, if you well, think a little bit about this differential equation, you will realize that, wow, that the growth rate cannot be proportional to the population forever, right? Because the bacteria only have limited resources. So otherwise, they would just increase faster and faster, and then eat up everything in the world, and then they would have to eat everything in the space, and so on. So this law is true only when resources are plenty. So only in the beginning, right? So I will write, in the beginning of the process, P, G. But later, as the colony of bacteria grows and they run out of food, so what's going to happen then? And here is a good model to account for bacteria running out of food. This is called the logistic differential equation. Logistic equation. Well, sorry, just try logistic. Let me explain the logic behind it. So suppose that we look at this differential equation. Sort of, we want to see what happens when t is small in the beginning of the process, right? So when t is small, I will write if t is much less than 1, meaning that t is small, then the population of bacteria is now very, very small also, which means P over K is almost 0. And if P over K is almost 0, it means that we don't have this term, and the remaining part is just this. dp dt equals rp, so which is the same as the equation before. But it can only be applied if the current population of bacteria, which is P, is really very small, is much smaller than K. Oh, sorry, if P is much smaller than K. So this happens if P is much smaller than K. And so let me write it again. So if P is much smaller than K, then this equation becomes just dp dt equals P. Because if P is much smaller than K, then the right hand side P over K, well, we can just neglect it, is almost 0. Well, but then eventually, this differential equation tells us that the colony of bacteria is growing. Now P is growing, and then eventually, of course, P is going to approach this K. So what's going to happen when P has almost reached K, when P is approximately equal to K? When P is approximately equal to K, then P over K becomes 1. And then in the right-hand side, we have 1 minus 1, which is 0. So then our differential equation, when P equals K, becomes dP dt equals 0. And dP dt equals 0 means that the growth rate disappears, right? So the growth rate is 0, so the growth has stopped, and our population of bacteria becomes constant. And of course, if it is constant, then it has to be just exactly K. And so in other words, this logistic differential equation would tell us that at first the population of bacteria is growing according to the law where the growth rate is proportional to the population, but eventually the growth rate goes down, and then the growth, this population of bacteria stabilizes and becomes almost K, or slightly less than K, and then the more time passes by, the closer it becomes to K. And so here is the logic behind this logistic differential equation. Well, then a little challenging question for you is the following: that if you try to figure out what a human population, which differential equation the population of humans satisfies, then you will see that it is actually proportional not to the growth rate is proportional not to the current population, but rather to the number of pairs of current population. So in other words, it is proportional to the square of total population. And here is a challenge for you. If you can figure it out, please, you're welcome to post your answers onto the online forum. Right? So that this growth rate cannot continue forever, even theoretically and even with unlimited resources. So the question is why? Why can't human